Welcome back to Past Journals. We are still continuing with our study of concurrent data structures, and we are looking at concurrent linked lists. So in the previous video, we looked at coarse-grained synchronization, and in this kind of synchronization, we saw that any thread attempting to perform an operation on the list will have to lock the whole list, preventing other threads from accessing it. Right away, you can see that this brings a challenge when it comes to throughput, because if we have a list that is long enough, then we assume that some threads will be working at very, very different areas of the list. So for example, if our list is 100 entries long, then a list performing an operation at the 20th entry should not be preventing a thread performing an operation at the maybe 50th entry, because these are far ahead of each other. So we have a few solutions to this, and one of them is fine-grained synchronization. So fine-grained synchronization suggests that we shouldn't be locking the whole list. Rather, a thread should be locking only the entries that it is looking at locally at a given point in time. For example, if we look at this kind of list where we have a head pointing to A, B, C, then a thread that is interested in thread A or thread B should be interested in this local view rather than the whole list. In other words, any thread that is interested in these two should not be locking the whole list, rather it should lock only the entries that it is looking at locally at that point in time. And again, we still have three operations. We have add, remove, and contains. So let's look at the add operation first. So for the add operation, we would like to see how we add a node to our list using fine-grained synchronization. So let us assume that we want to add a node B. Let's say our list is previously head to A to C. If we would like to add B, we will start by, start here at the head. We lock the head, and before we investigate A, we should lock A. That means we will hold two locks, the one at A, the head, and the one at A. And since A is okay, then we can move on. We see that B is greater than A, so we can move on to investigate A and C. Again, when we continue this, then we can drop head because we are not interested in head anymore, but we are still interested in A because it is the previous to the next node that we are looking at. Therefore, our next lock will be held at C, and therefore we'll be looking at A and C. And then we can see that B gets right in the middle of these two, so we can insert B right in the middle, and then we can move on. Okay. So we can see how the add algorithm works. We start by looking at the head because that's our entry, so we lock it, so we can see that the pred here is the head, and then the current is the next one. And we can see this while loop here is the one that traverses the list, and you can see that before we move on, we unlock the head. We unlock the previous node, and we don't unlock the next node, the current node. It's still locked. So we unlock the previous node, then we lock the next one in a process that we call handover locking. So we keep handing over locks again and again. So let's see why this is much more necessary when we look at the remove. And right away we see an example here. So we see that if we don't perform this handover locking, for example, coupling of locks, rather, if we say that, okay, a thread is interested in a node A, that is currently the one it's investigating, therefore we should only lock A, then we can look at two threads. The thread A is the first thread is interested in removing A, whereas the second thread is interested in removing B. So the thread that is interested in removing A will lock the head and try to remove A. then A is removed. On the other hand, the thread that is interested in removing B is here, therefore it will lock A and remove B. At the end, the global view of these two operations should suggest that at the end of these two operations we should be having head pointing to C. But because of remove A, we ended up pointing to B, and because of remove B, we ended up with a broken list, because now our A was pointing to C and head has no idea what this thread did. So the thread at head has no idea what this did, and the thread at A has no idea what this did, and we end up with a broken list. The suggestion here is that we need to do what we call coupling, and this is why it becomes very necessary. A thread that is at head here, before it investigates A, it should lock it. So by locking this, a thread that attempts to remove B would need to hold the lock at A first. But if it finds that another thread that is here is holding A as well, it cannot remove it. Therefore, if we try to remove A, we hold this lock and this lock, both of them at the same time, and that way we can be sure that we can connect right away to B. And that way a thread that was attempting to remove B by holding this cannot actually find it. The next time it tries to get the lock, it says that the node is no longer there, and therefore it will have to go back to the head and go through to find that we are actually pointing to B, and therefore remove B as well will be done in the same manner, and then the list remains intact. So for example, here you see that we hold these locks here and we perform what we call handover locking. I really encourage the viewers to go through this book. I think it's publicly available, so you can go through chapter 9 and try to understand this better, or if you have any questions you can leave them in the comments. So we go back to our remove algorithm. So if we go back to our remove algorithm, we can see it's not very different from what we did previously. We lock the previous head. So the previous starts with the head, we lock it. The current is the next, we lock it. We traverse the list doing some handover locking. So we unlock previous, then we lock next, which makes sense. So, and at the end of it all, we end up with here. After traversing and ending up at the node that we are interested in, we are here. So in remove, we see that if the key already exists, we remove it by just unlinking, and after that we can just continue to unlock both nodes. Okay, so this is going to present a challenge in Rust, as we will see how to perform handover locking. And that's going to be the biggest focus of this video. Let's see how we can implement this fine-grained synchronization in Rust. Right, we can see that from our previous implementation, the node has changed. In this case, we have the mutex lock inside the link itself. Previously, our mutex lock was on the head because we only needed to lock the head of the whole list. But in this case, we need to lock every node that we are looking at locally. And again, looking at our add function, for example, we can see that we start by getting the lock on the head, as we saw in the Java implementation, and then we try to investigate that lock. So the guard, by holding the guard here, we are locking the contents of the head, and then we try to investigate. So if the head exists, then we try to look at what's inside. So in this case, we see that we get the next. So I'm making the next global to this loop here because of what we shall see coming. But we assign next here, and then we get the next guard, then we investigate. I think this can be interchanged. I don't think it should be necessarily here. We can as well just put it right around here. But the important point is if the current node has the key, then we don't need to add the key here because we don't allow duplicates. Then next, if the current node's key is greater than the key we are looking at, then that means we need to interchange the keys. So we insert a new node, but that new node takes the current node's key, and then the current key that we are trying to insert is given to the node that we are looking at, and then we continue to assign next to the node that we have just inserted, and then we return true. And this is fine because, well, we don't expect a node to be forward to be looking backward anyway. So next, and then we have exclusive access to the current node. So we don't expect anyone to have stored prev, for example, in this case. Next, we look at inserting how do we move on from here? For example, in the Java implementation, we saw that we would require a handover locking. So in this case, this is the lock. So we would expect unlock and then getting the lock to the next. So we can see that next is already locked here. And at this point, we can say that, well, in order to perform a handover lock, then we should see the current guard taking over next guard. Unfortunately, this is not possible. So, for example, we cannot just say, well, current guard is equal to next guard. Okay. And you can see that, well, it does not live long enough. So one can say, even if we remove this, we can see that we already have problems, and we can see that this guard does not live long enough because guard will be dropped somewhere, and we see complaints right away. And there is, unfortunately, after searching for a while, I realized there is no safe way of performing a handover lock, and the only way that we can do this by performing a transmute. So if we do this, then the next guard will never be dropped, since it is taken by this function, assigning it to current guard, meaning that we still hold this guard, so it's not dropped, and therefore we don't drop our lock, and then we can continue. And this was the most interesting part for Rust, because as much as Rust is safe, I couldn't find a safe way that is already existent of performing the handover lock. Anyway, at the end of this while loop, we shall see that either we end up with an empty node, which we can now add, where we can now add our new node, or something will happen inside here and then we return inside. So the add function appears to work fine. Similarly, we can look at the remove function. So in the remove function, we do the same thing, only that this time, if we find the key that we are trying to remove, we can just assign the current guard to be equal to the next guard. So we take the next guard's value and we move on. So, and if the node doesn't exist, we can just return false. So as simple as that. I think this is much easier compared to the Java version, but understanding this step is crucial because it took me quite a while to get over this. So let us run some tests. We can see I have some tests here, the test for adding. So we can see, and right away we can see that our lazy step, the add, is okay. So I expect maybe if you're following, you can try it upon you to add the test for the remove function and check that it works fine. Thank you, and see you in the next video. If you like this content, please like